Hello, welcome in the 14th lecture of convective heat transfer. In this lecture, we will be discussing about once again thermally and hydrodynamically fully developed flow. But in the last lecture, as we have taken the heat flux of the wall of the tube was constant, here in this lecture we will be considering that the tube is having constant wall temperature. Okay. So, as I have said that our topic of this lecture will be thermally and hydrodynamically developed flow with uniform wall temperature. Okay. So, if you have to visit what happens in case of uniform heat flux, please see our last lecture. Okay. So, let me first tell you that what main points we will be covering over here. As it is thermally fully developed flow, first we will be recapitulating the conclusions whatever we have derived in our last lecture for thermally fully developed flows. Okay. And here we will be specifically seeing that what are the boundary conditions for fully developed flow we are getting. Okay. Next we will be applying this uniform wall temperature case. Okay. Here only we will be deviating from the last lecture. We will be applying uniform wall temperature and derive what is the energy equation in non-dimensional form. Okay. Then we will show you this energy equation is not easy to solve in analytical methodology. We have to go for some iterative solver. So, here I will be showing you how that numerical scheme can be taken and iterative solver how we can use for solving this energy equation whatever we have derived, and from there finally we will be getting that what is the temperature profile and Nusselt number. Okay. And at the end we will be showing you that what is the Nusselt number for thermally and hydrodynamically developed forced convection over a tube having constant temperature. Okay. So, these four things we will be seeing in this lecture. Next, let us start from this thermally fully developed zone. So, for that if you remember in our last lecture we have considered that temperature can be non-dimensionalized as T minus Tw by Tb minus Tw, okay, and that non-dimensional temperature quantity we have taken as phi. Okay. And we have also shown that this temperature as it is thermally fully developed, this temperature or non-dimensional temperature will be only a function of R. Okay. So, this we have already proved in our last lecture. So, from that conclusion only we will be starting over here. Now, as we are having uniform wall temperature in the present lecture, so obviously this Tw, okay, this Tw will be a constant value. Okay. This will not be varying with respect to the axial location as we have seen in our last lecture. Here Tw will be a constant value. So, little bit of side changing if we do, then we can get T equals to Tw plus Tb minus Tw into phi, which is a function of R only. Okay. It is not dependent on the Z because flow is thermally fully developed. Okay. With respect to Z, with respect to the axial location profile will not change. Okay. Then if we do the derivative of this temperature with respect to Z, then we can find out del Z of T as Tw is constant for uniform wall temperature. So, this term will be going to 0, okay, plus here as phi is a function of R, we need not to do the derivative of phi with respect to Z, okay, but here you see Tb minus Tw is there which can depend on the value of Z. So, here we need to do the derivative. Now, once again this Tw part is once again constant. So, that derivative does not make any sense. So, if we do the derivative of T with respect to Z, this is only coming over this Tb or bulk temperature. So, it will become ddz of dTb of dz, that means derivative of this bulk temperature with respect to Z multiplied by this phi R. Okay. So, we have seen over here del T del Z is equals to del dTb dz into phi R. Okay. Next, let us see our energy equation. We know that for a pipe, in case of a duct or pipe, the energy equation, simplified form of energy equation is like this, and this convection equation will be actually dropping two terms over here whenever we have fully developed flow. Okay. So, here you see we are having only W component over here, W del T del Z. W is nothing but axial component. Okay. In the convection side, and in the in the conduction side we are having our radial conduction as well as our axial conduction. Okay. So, here you see we are having we are actually neglecting the azimuthal component. Okay. So, and this alpha is nothing but thermal diffusivity, this we have seen earlier. Okay. Next, let us try to see that how this equation can be non-dimensionalized. So, for non-dimensionalization, in the left hand side we are having W. So, that W we are non-dimensionalizing with some average value of the W, W bar average into W. Okay. And del Z of T over here we have already seen that that is nothing but d dz of Tb into phi r. So, that value we have substituted over here. Okay. And in the right hand side, for the radial conduction side, we are taking out this Tb minus T infinity for making T to phi. Okay. And the axial conduction part we are using once again derivative of this one. So, second derivative of T will be becoming second derivative of Tb into phi. Okay. So, that we are keeping over here. So, from this equation we have actually found out this type of equation after changing del Z of T to del Z of Tb. Okay. Next, let us see little bit of side change. If we do, then this radial conduction can be written as W average r square by alpha into d dz of Tb by Tb minus Tw into W into phi. Okay. So, W and phi you can get from here, W and phi was there. Okay. And this d dz of Tb will be remaining over here. Okay. And for the axial conduction part which will be going in the other side with a minus sign. So, this comes over here and this axial conduction will be remaining as second derivative of the bulk temperature with respect to Z axial direction. Okay. Along with that we will be also having a phi over here. Okay. So, this is the radial conduction part, and here we are having this axial conduction, subtraction of the axial conduction from the convection part. Okay. Next, let us do little bit of further simplification. Here you see this term which is there in the first bracket, this can be written as in terms of your Peclet number. So, here what we have done, this minus Peclet number we have introduced. Okay. And R naught square was there. So, 1 R naught will be remaining. So, that R naught we have kept over here. Okay. And the axial conduction remained in the same form, only the sign change we have done. As a result, this minus sign became positive. Okay. So, this is more or less the equation. Now, already we have told you earlier this axial conduction can be neglected in case of thermally fully developed flow. So, in that case if this value is smaller compared to the other terms, that means radial conduction and convection term. So, this last term for the axial conduction can be neglected. So, let us take that assumption that neglect axial conduction, that means negligible axial conduction we are having. So, under that this term can be neglected. So, our equation actually simplified into this form, where in the left hand side we are having the radial conduction and in the right hand side we are having actually your convection. Okay. Next, let us try to understand what is the magnitude of this dTb dz. Okay. So, in order to do that, let us take a small control volume in our fluid element, okay, a cylindrical control volume in our fluid element, and there you try to understand the energy balance. So, if we try to do that, let us say that fluid element is surrounded by a fluid coil, a electrical coil or heating coil which is supplying heat flux Q. Okay. So, this heat flux Q will be received by 2 pi r0 is the perimeter into dz quantity. Okay, so 2 pi r0 into dz is the actual area through which heat is being supplied to that fluid element, and what amount of temperature change the fluid element will be causing, that is nothing but mCp into dTb. Okay. Now that energy balance, if you divide throughout by dz, so it comes out to be m dot Cp dTb dz equals to 2 pi r naught, dz will be cancelling. Okay. So from here you can further see that this dTb dz can be written as 2 pi r naught q divided by mCp, and m once again can be written as the mass of that fluid element whatever we have taken. So that is nothing but the density of the fluid multiplied by the volume. So the volume will be nothing but pi r square, pi r naught square, which is the cross sectional area of the duct multiplied by the velocity, average velocity w bar average. Okay. Little bit of cancellation of terms, you can get 2q divided by rho r naught w average Cp. So here you see only q is changing, which is a function of z. So we can say that this dTb dz is only a function of z. Okay, because q is a function of z only and rest parameters are actually constant. Okay. So we got that this dTb dz is actually a function of z. Okay, and as a result what you can do, the axial conduction second derivative of this one will be becoming actually once again a z function. Okay, which can be neglected over here. We have taken the assumption. Okay. Next, let us try to see that what this term in our equation is becoming. So let us try to simplify this one. So r naught divided by Tw minus Tb. So r naught divided by Tw minus Tb multiplied by this dTb dz. So dTb dz is over here. Okay, let us try to put this value of dTb dz whatever we have got in terms of q just before this. Okay. So we have put the same thing, you see 2q, now this Cp we have converted in terms of alpha and k. Okay. Rho and Cp is nothing but equals to alpha by k, that comes from the definition of thermal diffusivity. Thermal diffusivity alpha is equals to k by rho Cp. So from there we get this equation. So 2q rho Cp we have converted to alpha by k, and W average R naught remains over there. Okay. So little bit of cancellation if you do, and if we consider Q by Tw minus Tb is actually equals to H, heat transfer coefficient H. Heat transfer coefficient H is nothing but heat flux divided by the temperature change. Okay, average bulk temperature change. So you can write down this one as H. So ultimately this term whatever is in the first bracket over here you can write down 2H alpha by k W average. If you multiply 2 R naught at denominator and numerator, then you can find out this is actually one non-dimensional number, and here also we are getting another non-dimensional number. This is nothing but your Nusselt number H2 R naught by k based on the tube diameter, and here also we get the other non-dimensional number which is nothing but alpha W average into 2R0 by alpha, which is nothing but Peclet number. Okay. So we can write down this whole term as 2 Nusselt number by Peclet number. This 2 will be coming from here. Okay. So ultimately this term over here in the first bracket can be written as 2 Nusselt number by Peclet number. Okay. So if we proceed further, so our equation will be simplified like this, because earlier there was Peclet number by 2 and you are getting 2 Nusselt number by Peclet number, so Peclet number gets cancelled out. So ultimately you get del square d square phi d r square plus 1 by r d phi dr, which is nothing but radial conduction part, is equals to minus Nusselt number W phi. Okay. And subsequent boundary conditions will be coming like that. At r equals to 0, del phi del r is equals to 0, which is at the axis of the tube. Okay. So there will be no gradient of phi across the axis in the radial direction, and this is at the wall. At r equals to 1, phi will be equals to 0, because phi we have defined as T minus Tw by Tb minus Tw. So that will be becoming 0, because Tw minus Tw goes to 0. Okay. This is another boundary condition which we have obtained or we have found out at the wall, okay, at the wall r equals to 1 for our thermally fully developed flow. This has been proved in our last lecture. So, we are not going into detail of this proof of this one, we are straight away taking this equation from the last lecture. So, if you want to see the details of this one, please visit our last lecture. Okay. So, this equation actually will be helping us to find out the value of Nusselt number, okay, after solution of these sets of equations, right. So, let us proceed further. Before going there, let me introduce the bulk temperature. This also we have introduced in our 11th lecture, where we have shown that bulk non-dimensionalized bulk temperature can be written as 0 to 1 Wr phi dr divided by 0 to 1 Wr dr, okay. And bulk temperature definition is nothing but Tb minus Tw by Tb minus Tw, because phi we have considered as T minus Tw by Tb minus Tw, okay. So, we get from here that phi b is nothing but equals to 1. So, we can get the value of this integration is actually equals to 1, okay. And as we know that in thermally fully developed zone, W will be getting some sort of parabolic profile, Hagen-Poiseuille profile. So, if you put the value of W over here and integrate from 0 to 1, you will be getting the value of this integration will be half, okay. So, from here we get that 0 to 1 Wr phi dr is nothing but equals to half, okay. So, this will be required in the latter portion once we get the profile of phi, okay. Next, to solve these sets of equation and simplify this further, especially this equation, simplify it further, what we do, let us consider that phi is actually Nusselt number into f, okay. Here f and phi both are function of r, okay. So, if we do so, then you see from previous set of equation, here you see Nusselt number was minus 2 del r of phi at 1 comma z. From there we can write down Nusselt number is nothing but equals to half divided by 0 to 1 r w f dr, okay. And here little bit of multiplication with 2, we in the denominator and numerator we can get Nusselt number is nothing but 1 by 2 into 0 to 1 r w f dr, okay. Now, this r into f in r into w into f, that whenever we integrate from 0 to 1, that we have already written over here, this kind of equation will be coming over here, okay. So, let us see that how we can extrapolate or replace this phi with respect to f and reduce the sets of equation. So, if you do so in the previous equation, in these equations and these boundary conditions, if you put this phi equals to Nusselt number into f, then ultimately you will be getting this type of equation, d square f dr square plus 1 by r df dr is equals to minus Nusselt number wf. The equation will not be changing its form because in both sides, left hand sides and right hand sides, we are having f. Okay. Now, let us talk about boundary conditions. Here you see these two boundary conditions are more or less remaining same, whatever we have seen in the form of phi, only phi is being changed to f. But major change is coming over here. Earlier we have seen that in the boundary condition we had Nusselt number. Now, by replacement of this Nusselt number into phi into f, by this phi, we are changing this boundary conditions like this, that ddr of f at 1 comma z is becoming minus half. There is no Nusselt number in this equation, okay. So, now this equation along with this boundary condition is little bit typical to solve analytically, because in both the sides we are having f over here, nowhere we are having constant. So, this is little bit difficult analytically to solve. So, what we do, we take the help of numerical scheme. So, it needs actually iterative numerical scheme for solution, and that too we have to start from one initial guess, okay. So, let us see that what will be the numerical scheme to solve these sets of equation. So, here I will be presenting you some solution algorithm. So, solution algorithm at the beginning, as I have mentioned, we have to start from some initial guess. So, we set some parameter n, let us say n determines that what is the step of your guess, okay. So, set n equals to 0 and let us guess the value of f. A very authentic guess is nothing but all f at different r location is 1. Okay, you can start from any other guess, no problem. Okay, depending on your guess, number of iterations in between will be varying. Okay, so with this guess of f of r, what we can do immediately, find out the Nusselt number. Okay, already I have shown you that Nusselt number is nothing but 1 by 2 into 0 to 1 r w f dr. Once you have the value of f, so what we can do, w is also a known profile, so we can find out the value of this integration, and ultimately we can get the value of Nusselt number. So with the initial guess of f, we are doing the same, we first find out the Nusselt number. Okay, Nusselt number, and we are mentioning this Nusselt number as at level n equals to 0. So Nusselt number 0 is nothing but equals to 1 by 4 into 0 to 1 r 1 minus r whole square f0 r dr. Okay, so earlier it was 2, now the w profile is nothing but 2 into 1 minus r square Hagen-Poiseuille profile, so that is why it became 4. Okay, so once you compute the Nusselt number at 0th iteration level, then what you can do, you can try to solve the sets of equation whatever we are having. Let us show you once again the set of equation, this one. So what we will be considering in this set of equation, that in the right hand side we are having the value of f at the next iterative level, and in the in the left hand side we are having the value of the f at next iterative level, and in the right hand side we are having the previous iterative level. Okay, so here this f will be considered at previous iterative level. So in that same way, and here you see, if you multiply the whole equation with r, then you will be finding out this term can be written as ddr of r df dr. Okay, so you see, if we do the derivative of this equation, then you will be getting actually df dr plus r del square f r d square f dr square. So that is nothing but if you multiply this equation with r, then you will be getting the same thing. Okay, in the left hand side at least. In the right hand side, you see we are taking the same thing, r multiplication is over here, but in this side we are considering f based on n iteration level. In the left hand side we are having n plus 1th iteration level. So for n equals to 0, this will be f0 and this will be f1. Okay, so once we get this equation, this side is becoming a constant, making the integration of this equation and find out the value of f1 or fn plus 1 will not be difficult. So once you get the value of f, then next task is to find out or if you have to actually get the values of f using this boundary conditions also. These boundary conditions, whenever you will be integrating this one, will be required. Okay, so at r equals to 0, dfn plus 1 dr is equals to 0, and at r equals to 1, f of n plus 1 equals to 0. Okay. Next, once you determine the value of n plus 1, f of n plus 1, next task is to get the value of updated value of Nusselt number. Earlier you had Nusselt number at n, now we will be finding out a Nusselt number of n plus 1 using the value of f n plus 1. Okay, so that we are doing over here using the same formula, 1 by 4 into 0 to 1 r 1 minus r square f n plus 1 dr. Here we are putting the value of f at n plus 1th iteration level. Okay, so once you get the new Nusselt number, so you have now two sets of Nusselt number, one is at the old time step, another one is the new time step. I should not say time step, iteration steps. So you have to compare those. Okay, the two values of Nusselt number and check for convergence, whether you have obtained some converged solution or not. Okay, because you have started from initial guess with respect to progress in the iteration number, you will be reaching to the convergence. So let's say we have set some sort of limit epsilon which is very small. Now if you find out that between two Nusselt numbers we are having difference very small, okay, smaller than the limit whatever you have considered, then we can say that our scheme has converged. From here what you can do, you can check this criteria and you can actually find out whether it has satisfied or not in this condition. If it is not satisfied, then what you need to do, just make n equals to n plus 1 and go to step 3. Step 3 is nothing but once again solving this equation. Okay. So, for example, you have started with 0 and found out f1 and you have got that Nusselt number at 1th iteration level minus Nusselt number of 0th iteration level is actually bigger than some small value, epsilon value. Then what you need to do, you need to make that 0th level to 1th level and then once again solve this equation for f2. Okay. So, in this process f2 will be giving you f3 and so on. If you proceed it further, at some point of time you will be finding out that your condition for checking of convergence is satisfied. That means you have reached to some steady Nusselt number value. So, in that case what you do, you find out what is the value of phi by multiplying that Nusselt number with f, because whenever you come out you are having a new value of Nusselt number and new value of f, you can multiply these to find out the value of actual phi, okay, and subsequently you can print the value of Nusselt number and phi. Okay. So, if you follow this procedure, write a small numerical code, then you will be finding out that for this type of situation where we are having thermally and hydrodynamically fully developed duct with constant wall temperature, in that case the program is actually being converged and finally the Nusselt number will come out to be 3.657. Okay. So, this Nusselt number whenever you are printing, this will come out to be 3.657. Okay. So, this is very important, Nusselt number for constant wall temperature duct at thermally and hydrodynamically fully developed region is 3.657. Okay. So, let me summarize what we have understood in this lecture. So, first we have understood what are the governing equations for thermally and hydrodynamically fully developed forced convection inside a tube having constant temperature. Okay. So, the equations are like this, we have seen in terms of f, where f is nothing but your phi by nu, okay, Nusselt number, and we have got this boundary condition. The last boundary condition has been modified by introduction of Nusselt number, and by using numerical scheme, iterative numerical scheme, I have showed you that how to solve these sets of equation, and finally we have mentioned that if you solve this equation by iterative scheme, the Nusselt number comes out to be 3.657. Okay. Just like other lectures, let us also test your understanding at the end of this lecture. So, we are having 3 questions once again. First question goes like this: in thermally fully developed region with constant wall temperature, axial conduction is negligible, becomes significant, you cannot neglect, becomes minus Nusselt number omega w into f, or D, A and C both. Okay. So, already we have done elaborate discussion on this. So, probably you can understand that now axial conduction can be neglected, okay, and we have neglected that one to obtain the equation of f, okay, finally, which I have shown you in the last slide in the summary. And the second question goes like this: in thermally fully developed region with constant wall temperature, which quantity remains constant? Okay, we are having 4 options: H, Tw minus Tb, both or none. Okay. So, obviously the correct answer will be only H remains constant. Okay. Then last question is like this: in thermally fully developed region with constant wall temperature, value of Nusselt number is 3.657, 4.3636, 5.7831 and D is none. In the last slide we have actually derived that one. So, the value is 3.657. Okay. With this I will be ending this lecture. So, please visit our next lecture, which is about thermal entrance region, okay, and that too we will be considering at uniform wall temperature. About this lecture or about any other confusion, if you are having any doubt, please keep on posting in our discussion forum. Thank you.